Assalamualaikum warahmatullahi wabarakatuh. A very good day. So for this part, we will discuss about the specific heat. Specific heat. So the meaning of specific heat is the energy that required to raise the temperature of a unit mass of a substance by 1 degree. So which means we want to know the amount of energy if we want to increase the temperature of the substance by 1 degree. So that's the meaning of the specific heat. So there are two types of specific heat. First, we have specific heat at constant volume, where in terms of symbol represented by CV. So in order to describe the process or the experiment in order to obtain the CV value, so we have a rigid tank. Okay, let's say for example this one for helium. So inside the rigid tank we have helium gas, where for this condition V will be constant. Let's say mass equal to 1 kilogram. So we want to increase the temperature in terms of delta T equal to 1 degree. So for this helium, in order to increase 1 degree Celsius, so we need to supply 3.12 kilojoule of energy. Okay, so due to the definition of specific heat, so now the value of CV, specific heat at constant volume for helium, will be equal to 3.12 kilojoule divided by kilogram degree Celsius, and the value actually is same as the value of energy that supplied to the helium gas in the rigid tank when the temperature increased by 1 degree Celsius. So in terms of relationship, or in terms of formula, in mathematical formula, the CV actually equal to du over dt. Okay, so bracket, we have V here to show that the process involved is constant volume. So the value of CV relate to the internal energy difference with the temperature. So we can derive, or we can define more for the CV in detail. So CV, specific heat at constant volume, actually is the change in the internal energy of a substance per unit change in temperature at constant volume. So this is the specific definition for specific heat at constant volume, CV. The second one, we have specific heat at constant pressure, and the symbol that we use is CP. Okay, so in order to describe the value of CP for certain substance, so we will use this kind of diagram. We use cylinder piston device, where the piston freely move in order to maintain the pressure. Okay, when the piston freely move, so if we add heat to the substance inside the cylinder, so we can control the pressure at constant pressure. And let's say the mass is equal to 1 kilogram, and the gas also the same, which is helium, for example. And we need to supply, we want to know how much energy that need to supply in order to increase the temperature of the helium by 1 degree. So here the amount of energy that we need to supply in order to increase 1 degree Celsius of temperature for helium gas is 5.19 kilojoule. So that's why the value of CP for the helium is equal to 5.19 kilojoule per kg degree Celsius. So the value of CP represent the amount of energy during the constant pressure in order to increase 1 degree Celsius in terms of temperature. And in terms of relationship, so CP relate to the enthalpy change with the temperature, and we have bracket P just to represent that the process involved is constant pressure. So the detailed definition for specific heat at constant pressure is the change in the enthalpy of a substance per unit change in temperature at constant pressure. So if you look to the both type of specific heat, for specific heat at constant volume, CV, so the CV value will depend on the internal energy value. However, for the CP is called related or affected by the value of enthalpy difference, okay, delta H. Okay, now we want to discuss about the relationship between internal energy, enthalpy, with the specific heat for the ideal gas. Okay, ideal gas. Okay, for example, now in terms of relationship between internal energy with specific heat. So for this case, we need to implement the energy balance equation. We need to apply the energy balance equation to the what we call the schematic diagram that we discussed just now for the specific heat at constant volume, which is referred to the rigid tank. Okay, so if we simplify the energy balance equation for that system, so at the end we will get the simplified energy balance equation where Q in equal to delta U. Okay, we just ignore whatever E mass in, E mass out, W in, W out, based on the system schematic diagram. So we have Q in equal to delta U. Okay, now the equation can be changed to du equal to cv bracket t dt. As we know that the value of Q in for this specific heat case is actually equal to the amount of heat Q in that's applied to the system, actually equal to the value of Cv. That's why instead of we have Q in, we have du equal to Cv t, where CVT dt actually is referred to the amount of energy during the what I call the process where we want to increase 1 degree in terms of temperature of the substance inside the rigid tank. Okay, so CVT dt actually is the amount of energy that's applied to the system during the experiment or the system that involve with specific heat at constant volume, where we want to increase the temperature by 1 degree. For the case where very specific heat with temperature, okay, after we make integration, so actually this process or this equation actually is the basic of the data in the table for the ideal gas. Okay, this one where delta U equal to U2 minus U1 equal to integration of CVT dt from state number 1 to state number 2. Okay, so this equation for the variation of specific heat with temperature, which means that the value of Cv will change if the temperature change. So we need to use the integration equation. However, for constant average specific heat with temperature, we can use the equation where we call the internal energy difference U2 minus U1 equal to Cv average multiplied by temperature difference T2 minus T1. So the value of Cv average actually we can obtain from the table in what we call thermodynamic books, any thermodynamic books, where this value Cv average can be obtained for different type of gases. Okay, now in terms of the what I call the relationship between enthalpy and also the specific heat, so now we need to base on the what I call the schematic diagram for the specific heat at constant pressure above. Okay, so we need to implement the energy balance equation in order to obtain the relationship. So after we what I call the simplified equation, so we'll get, because the schematic diagram involved with the moving boundary, so we have the term for moving boundary. So our Q in will be equal to delta U plus work boundary or boundary work, WB, and the formula for WB actually same as the pressure multiplied by delta V. So we have Q in equal to delta U plus P delta V, and delta U plus P delta V actually is the definition or is the formula for delta H. So now the Q in will be equal to delta H. So we can get the relationship in terms of dH equal to CPT dt. Why? Because during the process when we want to determine the specific heat at a constant pressure, we need to supply amount of energy that to increase the 1 degree Celsius of substance. So the value actually same as the value of Cp during the process. So we just substitute, instead of we use Q in, we use CPT dt, because the value is the same when we consider the energy that required in order to increase the temperature of the substance inside the system by 1 degree. Okay, so we have Q in, and the value of Q in actually is equal to Cpt dt. Okay, so the various specific heat with temperature, if we integrate the equation, so we will get the what we call the equation for delta H and also Cpt. So this equation will use as the basis or as the basic equation to determine the data for the thermodynamic table for the ideal gas. So we have delta H equal to H2 minus H1 equal to integration of Cpt dt. So for this equation, the value of Cp is not constant, where the value of Cp will change if the temperature change. Okay, and then for the constant average specific heat with temperature, we have this formula where the value of Cp constant not depend on the temperature. So H2 minus H1 equal to Cp average multiplied by T2 minus T1. Okay, so same as the value of Cv average, Cp average also we can obtain from the table in thermodynamic textbooks for different type of gas. Okay, now about the Cv and also Cp relation. So we have the relation between Cv and Cp, where specific heat relation we have combination of Cp and also Cv, where Cp equal to Cv plus R. R stand for a gas constant. And we have the ratio term of specific heat that we call K, or we call specific heat ratio K equal to Cp divided by Cv. Sometimes in order to simplify the equation, we will use the what I call the symbol of specific heat ratio. Okay, so U and H, internal energy and also enthalpy determination for ideal gas. There are few ways in order to few ways to determine U and H for the ideal gas. First, we can use ideal gas table, and this method actually the easiest and the most accurate approach in order to obtain the value of U and also H. The second one is by using the equation related to Cv and also Cp as a function of temperature. Okay, which is the formula involved with integration. And this approach slightly tedious but very accurate. Okay, so keep in mind that actually the method, the approach number one, which is the table, the data actually come from the equation that we use in approach number 2, where we use the equation that involve integration. Okay, however, for approach number 1, we will use some sort like the numerical approach. And okay, so for approach number 2, we can use this equation for the internal energy. We can use delta U equal to U2 minus U1 equal to integration of CVT dt. And for enthalpy, we can use delta H equal to H2 minus H1 equal to integration of CPT dt. Okay, the third approach, we can use equation related with average specific heat, Cv average, and also Cp average. And this approach or method actually is simple, and in terms of value, we can say that the value is reasonable accurate. But in terms of error, this method for sure in terms of error percentage will be greater compared to method number 1 or approach number 1 and also approach number 2. For the equation that involves Cv and also Cp average, so we have internal energy U2 minus U1 equal to Cv average multiplied by T2 minus T1. And for the enthalpy, we have H2 minus H1 equal to Cp average multiplied by T2 minus T1. Okay, so this is the explanation for specific heat in terms of definition, equation, and also the approach that can be used, okay, for the ideal gas. So we have here the relationship in terms of internal energy, enthalpy, and also the specific heat for the ideal gas. Okay, later on we will discuss about the internal energy, enthalpy, and also specific heat relationship for solid and also for liquid. Okay, now let's look at the example for the specific heat. Example 3.7. Air at 200 Kelvin and 300 kilopascal is heated at constant pressure to 600 Kelvin. Determine the change in internal energy of air per unit mass using A. Data from the air table, and B. The average specific heat value. So we need to solve the problem to determine the internal energy for the air. So our substance now is air, and we need to use different approach. A, by using the table, and the second one by using the average formula. So in terms of data given, in terms of substance, the substance is air. Temperature given T1 equal to 200 Kelvin, P1 equal to P2, because in the example, in the question mentioned about the constant pressure equal to 300 kilopascal. T2 is equal to 600 Kelvin, and now we need to determine what called the internal energy change, delta U, in terms of unit per unit mass. So the unit will be kilojoule per kg. Okay, first by using the data from the air table, so we need to check in the ideal gas of air table. So if we look to the table, so we will have the ideal gas for air. So in the table we have numbers of data such as the temperature, enthalpy H, relative pressure PR, internal energy U, relative volume VR, and also entropy relative to 0 degree as degree. So we already have the temperature for state number 1 T1, and also the temperature for state number 2 T2. So we just based on the temperature given, so we can determine from the table for T1 equal to 200 Kelvin. So we can obtain the value of U directly from the table. Okay, at T1 equal to 200 Kelvin, so we'll get U1 equal to 142.56 kilojoule per kg. Okay, however, for T2, so we need to find the value for 600 Kelvin. Also, for the temperature of 600 Kelvin, we can obtain directly from the table, where the value of U2 equal to 434.78 kilojoule per kg. Okay, then in order to get the change in internal energy per unit mass, so we just subtract the value, where delta U equal to U2 minus U1. So substitute the value that we obtain from the table, so we'll get the value of delta U for the first approach is equal to 292.22 kilojoule per kg. Okay, done for question A. Okay, for question B, we need to use the equation involve is average specific heat value. Okay, so because now involve is internal energy, we need to use the average specific heat equation at constant volume. Okay, as constant value. Okay, change in internal energy per unit mass, so we have delta U equal to U2 minus U1 equal to CV average multiplied by T2 minus T1. See, okay, so in this equation, in terms of temperature unit, so we can use both, whether you choose to use Kelvin unit or you can choose degree unit, because in the equation involved is temperature difference. So the temperature difference for degree Celsius and also for the Kelvin is the same. So you can use any type of unit for the temperature. Okay, average heat in table. So now, in order to use the equation, so you need to know CV average value for the air. So in order to do that, to get the data, so you need to refer to the specific heat in table for specific gas or specific ideal gas. So for this case, you need to refer to the CV average value for air. Okay. Okay, so for this case, we have the specific heat at various temperature for air. So now, because the table refer to the temperature, so now in order to get the value, so you need to get the average temperature between temperature of T2 and also temperature of T1. So first calculate the average temperature. So T1 plus T2 divided by 2, so we'll get equal to 400. So from the value of T average, so we'll use this value to obtain CV value from the table. Okay, directly we can obtain where CV average at 400 Kelvin equal to 0.726 kilojoule per kg Kelvin. Okay, and then substitute into the equation. So you'll get the value of delta U for the second approach is equal to 290.4 kilojoule per kg. Okay, second example for this specific heat. So we have example 3.8. An insulated rigid tank initially contains 0.7 kg of helium at 27 degrees Celsius and 350 kilopascal. A pedal wheel with a power rating of 0.015 kilowatt is operated within the tank for 30 minutes. So determine the final temperature and also the final pressure of the helium gas. Okay, so now we just draw simple spectral diagram. So we have what I call the rigid tank. Surrounding the rigid tank we have insulator in order to prevent what I call any heat in or heat out. So this process actually involves the adiabatic process. So the temperature given T1 equal to 27 degrees Celsius, mass equal to 0.7 kilogram, and pressure P1 equal to 350 kilopascal. And the amount of power that provide to the system due to the rotational movement of the shaft is W shaft dot equal to 0.015 kilowatt. Okay, now data given. So the substance is actually helium. Okay, the substance is helium. T1 equal to 27 degrees Celsius and P1 equal to 350 kilopascal. So the time for the what I call the pedal wheel operate is for 30 minutes, and we need to determine the value of T2 final temperature and also P2 the final pressure. Okay, for the final temperature T2, so we need to implement the energy balance equation to the system. So we just write down the full equation and then decide which energy terms that not involved in the equation based on the schematic diagram and based on the system. So no Q in because the system is well insulated. No Q out. So we have W in due to the what I call the work into the pedal wheel. So we don't have any W out, and no mass in, no mass out because this system is a closed system, and we don't have any delta KE and also delta PE due to the stationary system. So the remaining term is W in equal to delta U, where W in here in this case is shaft work. Okay, now the shaft work, if we elaborate more, equal to delta U equal to M multiplied by U2 minus U1. Okay, so the question doesn't mention any specific condition whether you need to use the table for the helium or the specific equation. So now, because we want to know the temperature, so we will use the second equation involve with the equation that involves with average specific heat. Okay, because internal energy involved in the equation of shaft work, so we need to use the formula for CV average, where shaft work equal to delta U also equal to mCV average multiplied by T2 minus T1. And the shaft work, because the data for shaft work not given directly, so the data that we have for the example is the power for the shaft work, where we have W dot shaft which is equal to 0.015 kilowatt. So we can obtain shaft work by manipulating the equation, this equation where W shaft equal to W shaft dot multiplied by delta T. So we just multiply the power that provide to the system multiplied by delta T 30 minutes and change the 30 minutes to 1800 seconds and substitute into the equation. So we'll get shaft work equal to 27 kilojoule. Before we continue to solve the problem, we need to know the average specific heat for the helium. For this case, we need to refer to the ideal gas specific heat of various common gas at 300 Kelvin. Okay, so we have what we call the table in terms of properties, in terms of CVCP at constant temperature. Where for helium, so we have what I call numbers of data for different type of gas. Okay, for helium, we will have CV average for helium equal to 3.1156 kilojoule per kg Kelvin. So this is from the table. So we can get this table from any thermodynamic books. And then for the final temperature T2, based on the equation for the shaft work, first we rearrange the equation because all the data are already obtained except the value of T2. So we rearrange the temperature, the equation, and we have T2 equal to W shaft divided by MCV average plus T1. Okay, so subject to all the data that we have, so we'll get the value of T2 equal to 39.38 degrees Celsius. Okay, however, the last question is about the final pressure P2. Okay, so because this is a gas, helium gas, so we can use the ideal gas relation where we have P1 V1 divided by T1 equal to P2 V2 divided by P2. So for rigid tank, okay, from rigid tank, the condition is the volume is constant where V1 equal to V2 from the ideal gas relationship. So we can rearrange the equation so that we will get the equation for P2 where P2 equal to P1 multiplied by V1 multiplied by T2 divided by T1 multiplied by V2. So as we know, because the volume V1 equal to V2, so we can cancel out the term for V1 and also V2 in the equation of P2. So we have P2 equal to P1 multiplied by T2 divided by T1. Substitute all the value, but we need to make sure that for the ideal gas relationship, the equation when involved with temperature, the temperature must be in Kelvin unit. So we need to change from degrees Celsius to Kelvin unit. So we have 350 kilopascal multiplied by 39.38 plus 273 divided by 27 plus 273. So the pressure, the final pressure for P2 equal to 364.44 kilopascal. Okay, next example, example 3.9. A piston cylinder device initially contained 0.5 meter cubic of nitrogen gas at 400 kilopascal and 27 degrees Celsius. An electric heater within the device is turned on and is allowed to pass a current of 2 ampere for 5 minutes from 120 volt source. Nitrogen expands at constant pressure and heat loss of 2800 joule occur during the process. Determine the final temperature of nitrogen. Okay, so you need to know the final temperature of nitrogen. Okay, so draw the simple schematic diagram. So here we have cylinder piston device. We have electric heater. For the electric heater, we have in terms of ampere 0.2 ampere, voltage 120 voltage, and run for 5 minutes. So this is represent actually the data involved with the electrical work. And inside the cylinder we have nitrogen gas V1 equal to 0.5 meter cubic, T1 equal to 27 degrees Celsius, and P1 equal to 400 kilopascal. So for this case, the pressure is constant and the piston move in order to maintain the pressure. So we will have the moving boundary. So for this case we will have work boundary, and during the process we have Q losses to surrounding, which is equal to 2800 joule, 2800 joule. Okay, now in terms of data given, the substance is nitrogen, V1 equal to 0.5 meter cubic, P1 equal to P2 equal to 400 kilopascal because the process is constant pressure, T1 equal to 27 degrees Celsius, I equal to 2 ampere, voltage 120 volt, time running for the heater is 5 minutes, which is also equal to 300 seconds, and Q loss equal to 2800 joule. Now we need to determine the temperature of T2. Okay, so again we implement the energy balance equation. Write down the full equation for the energy balance, and then the next step you need to what I call simplify the equation by identify the energy that not involved in the equation. Okay, so for based on the schematic diagram and also the boundary, so no Q in, So we have Q out, we have W in, and also W out. No EMS in, no EMS out due to the closed system, and no delta KE, no delta PE due to the stationary system. So the remaining terms for the energy balance equation is negative Q out plus W in minus W out equal to delta U. Okay, so then make it more specific. So just replace the symbol, suitable symbol that for the energy based on the schematic diagram. So we will have WE electrical work minus WB the boundary work minus Q loss equal to delta U equal to U2 minus U1. And we know that the work boundary or boundary work formula for the constant pressure will be WB equal to P naught constant pressure multiplied by V2 minus V1. Okay, so just substitute the equation of WB boundary work into the energy balance equations for the system. So we have WE minus P naught multiplied by V2 minus V1 minus Q loss equal to U2 minus U1. Okay, so rearrange the equation. Okay, so we get WE minus Q loss equal to U2 minus U1 plus P naught multiplied by V2 minus V1. And this equation, actually, if we rearrange the equation, so we'll get the value of U2 minus U1 plus P naught multiplied by V2 minus V1 actually is the term for the enthalpy difference, H2 minus H1. Okay, so we change slightly the equation in terms of enthalpy. So now we want to use what I call the specific enthalpy, which symbol small letter H, and we need to involve the mass of the nitrogen. So WE minus Q loss equal to M multiplied by H2 minus H1. Okay, so now as we learned before, so because the question doesn't mention whether we need to use value of Cp is varies with temperature or not, or the question doesn't mention any approach that we need to use, so we can use what I call, instead of we use the table to determine the enthalpy, so we can use the formula involved with Cp. Okay, average Cp. Okay, so now we WE minus Q loss equal to mCp multiplied by T2 minus T1, because the equation involved is enthalpy different. Okay, so before we solve the what I call the value of final temperature of the nitrogen, we need to know what is the value of WE, because the value of WE not given directly in the question. Okay, so where WE electrical work equal to V multiplied by I multiplied by delta T. So all the data already given, so just substitute in the equation of electrical work. So we'll get the electrical work is equal to 72 kilojoule. And next, because in the equation we have the term for Cp for the nitrogen, again we need to refer to the I call the ideal gas specific heat of various common gas at constant temperature of 300 Kelvin. So then the nitrogen, we will have the data for nitrogen in terms of the value of Cp, where also we need to use the value of R gas constants, where R equal to 0.2968 kJ per kg Kelvin, and Cp for the nitrogen is equal to 1.039 kJ per kg Kelvin. Mass for the ideal gas of nitrogen, so we can obtain from the formula for formula for the ideal gas, which is PV-MRT. Okay, so M P1 V1 equal to M RT1. So we just rearrange to obtain the formula for mass. Okay, so mass for the nitrogen equal to P1 multiplied by V1 divided by RT1. So just substitute the value that we have. So remember the temperature, the unit for the temperature for the ideal gas formula must be in Kelvin. So mass equal to 2.246 kilogram. Okay, now we concentrate to solve the final temperature T2 based on the equation of the energy balance. So we have this equation for the energy balance, WE minus Q loss equal to mcp T2 minus T1. Okay, rearrange the equation so that we can get the equation for T2. T2 equal to WE minus Q loss divided by mcp plus T1. Cp here refer to Cp average. Okay, substitute the value, so we'll get temperature for T2 equal to 56.65 degrees Celsius or 329.65 Kelvin. Okay, so the temperature will be 329.65 Kelvin or 56.65 degrees Celsius.